So great. Welcome to another week's intercontinental seminar. This Wednesday we have with us Martin Krššák from Comenius University in Bratislava. Martin got his PhD in Bielefeld, if I remember correctly, in Germany, and then he moved to let me remember now, Sao Paulo, Brazil, with José Pereira, and then Tartu. Then we met together in Yangzhou in China. After that, he went to Chulalongkorn in Thailand, and now he's a Marie Curie Fellow at the Comenius University. And soon he will become permanent there. So today he's going to talk about self-excited gravitational instantons. And Martin, yeah, the floor is yours.
Okay, so thank you very much for this invitation to be here at the Intercontinental Seminars. So today my topic will be I will talk about the so-called self-excited gravitational instantons. So I will try to explain kind of each part of this three words there, except gravitational. Gravitational should be kind of obvious. And I will start first with some like a brief introduction. What are instantons and why we are interested in instantons? And then I will try to show you how we can have some kind of new kind of construction of some new gravitational instantons, which I call self-excited, and it will be quite obvious why I call them self-excited. It's based on this one paper, which is still not published, but it's currently under the review, so it looks very positive. Let's see the outcome of the review process, but you can find all the details basically here. So since this is a gravity and cosmology seminar series, so usually people in gravity, they are not so familiar with instantons or what are the instantons in quantum theory or quantum field theory. But basically all of us kind of remember this idea that if you have this path integral formulation of quantum theory, so basically you have all these possible paths, right? And basically then what you are doing is that each path to this path integral is contributing proportionally to its I of this action, right? So if you have some particle moving in quantum theory, this means that each path is contributing proportionally to its action. Well, in field theory, it's kind of the same. It's a little bit more complicated. Like what means even this integral, it's not completely clear. But anyway, it's something what people like to do. And then each of this path is not the path of a particle, but it's each kind of field configuration which we can have. And usually when we do this in quantum field theory, we don't do this in a Lorentzian case. What we often do is we do so-called Dicke rotation. And these oscillating integrals, we just do a Dicke rotation to some imaginary time. And then all these oscillating integrals, they turn into some like more nicely convergent exponential integrals, right? So basically, then when you see that this Euclidean path integral, something like this, then from here you can immediately see that only those solutions of your field theory which have some finite Euclidean action, they will contribute, like in some semi-classical approximation, they will have the major contribution to this Euclidean path integral, and they will be the dominant contribution in this approximation. And that's basically these finite Euclidean action solutions. That's what we call instantons. And this is something that was discovered in the 1970s in the Young-Mills case, and it's a very big part of the success and the story of Young-Mills theories. And there was a lot of interesting stuff done about Young-Mills instantons. So I will briefly introduce these Young-Mills instantons. But for me, the main question is, can we do this instanton construction, which was so successful and interesting in Young-Mills case? Can we do it in gravity? And well, I will try to show you that we can do it. Well, part of it was already done. And we can do it also some new way. And that's what I will be talking about. So basically, so what is Young-Mills theory, right? So I will be using this fancy language of differential forms because everything is very nice there. You have almost no indices. Basically, Young-Mills theory, and I'm a little bit vague what I mean by Young-Mills theory. Generally, I mean some SUN non-abelian gauge theory. I don't need to specify which SUN I mean. So what does it mean is that I have some connection one forms. From this connection one forms, I define some field strengths, usually just by the equation like this, right? And if I have some field strengths of these connection forms, these field strengths in Yang-Mills theory must satisfy this, what we call sourceless field equations. And I put it in quotation field equations because usually this first, which is this df, which is this exterior covariant derivative of f, which means like that dx like this on f plus, put there this term like a wedge f. This actually this first equation is not really field equation, is more like Bianchi identity. And then there is a second, this set of field equations, which is actually a field equation, which is the exterior covariant derivative of Hodge star f equals 0. And this field equation actually comes from some Yang-Mills action, and it's actually a field equation coming from some variation principle. So this is usually what we consider like action of a Yang-Mills theory. Modulo some overall terms, which I'm not putting like some, there are usually some 1/4 or -1/4. I don't care about such coefficients at this moment. So basically, that when you have this kind of field equations, you can ask, how do I solve these field equations? And well, there are many ways how to solve them, but there is one particularly clever way how to solve this set of second order field equations for A, which are really complicated. There is one very clever way how to solve them, and that was introduced in 1975 by Belavin, Polyakov, Schwarz, Yupkin. And basically, their idea was something very, very clever. Well, is that consider ansatz such that your field strength equals plus minus star of f. Star is this Hodge operator. So consider such ansatz, which they call self-dual or anti-self-dual ansatz, where the field strength is plus minus its dual field strength. And if your f obeys, so if you have such A which obeys this equation, then it's quite interesting what happens, because if you have some A, it's automatically must obey the Bianchi identity. So its df must be automatically 0. But if f equals plus minus star f, then this self-dual f also satisfies this second set of the field equations. So it means that you can, by having this ansatz, you can immediately solve not just the Bianchi identity, because you can also solve the field equations. So this is what people usually call that this self-dual f are what we call automatic solutions of Yang-Mills equations. And it simplifies the problem, because instead of this set of second order partial differential equations, a set of two second order field equations, you have to only solve this ansatz, which, well, it's quite difficult to solve actually, but you have to just solve this equation, which is only a first order differential equations for A. So you simplify this problem. And that's quite interesting. So it's a nice property that this automatic solution, these self-dual solutions are automatic solutions of Yang-Mills equations. And you simplify your problem because you turn a set of second order field equations into a first order differential equations, which is nice. But something interesting happens. And that's what interesting happens is that this action, which we had here, right, which was f wedge star f, if we consider that f is star f, right, this turns into this so-called self-dual Yang-Mills action, which is just this. And there's something particularly interesting about this action, because this action is just a topological term, right? So you can show that this self-dual Yang-Mills action is a topological term, and this topological term means that it is actually proportional to the divergence of something what is called Chern-Simons form. And the integral of this Chern-Simons form, you have this integral over d of this Chern-Simons form. You can turn it into a, using Stokes' theorem, you can just turn it over to some surface integral over the boundary of this space. And then you will find out that these integrals of these for some well-behaved connections, I don't want to go to the details, what does it mean, that you will find that actually this integral will turn out to be 8 pi squared times k, where this k is some integer number, which is usually no binding number or instanton number, or sometimes in mathematics, that's what people call it, second chair number. So the idea was that, so why is this interesting? Because we are looking for finite Euclidean action solutions from this construction which I just presented. It's obvious that if I consider this kind of field strength, there will be solutions of the field equations. But now, by this magic of topology, what turns out is that I prove that it's not just the solution, but actually it's integer. It's actually the action is not only finite, but it's actually proportional to some integer. So that shows that it's actually finite, right? It's proportional to some integer, which is characteristic to the group which we are considering. So this is actually quite interesting because this turns this problem of finding some solutions of these Yang-Mills equations into a problem related to topology. And so this is a very nice property. And then the second nice property is that you can actually show that such solutions which have this f plus minus star f property, so that are the self-dual solutions, they turn out to be a global minima, because we know that if something solves the field equations, it's some at least local minimum or local critical point of the action. But you can show, and it's actually quite easy to show, that these Yang-Mills action, which we had here, the original one, this one, it's always larger than the absolute value of this. This is usually what people call Bogomolny press of Sommerfeld bound. So basically, this means that in Yang-Mills theory, the self-dual BPST instantons, they have these three really nice properties. That they are the automatic solutions, they are topological solutions, and they are absolute minima. So it means that they are the dominant contribution to this path integral which you are considering. And this plays a very important role then in quantum field theory. There are many, it gives us many important insights about this non-trivial vacuum structure. Then as Stu showed, it means that there are some tunneling effect between these different vacuum states. And mainly it shows us some deep connection between physics and topology of gauge fields, which is quite interesting. And also then you can make this topology, this term which is topological, you can just make it dynamical, and that's usually leads to axial, which is one of the possible candidates for dark matter. So basically, this is what was done 40 years ago. Most of this was 40 years ago, done in Yang-Mills theory. But around the same time in the 1970s, mainly people, I mean Hawking, they wanted to do the same kind of construction, which was just discovered in Yang-Mills theory. They wanted to do the same in gravity. So Hawking in 1976-7, he started what is what's called Euclidean path integral approach to quantization of gravity. So basically the idea was, well, let's follow the success of Yang-Mills theory and try to quantize using path integrals, Euclidean path integrals. So let's quantize gravity. So there turns out that if you want to do this, it turns out that this gravitational action which you want to usually quantize, or which you want to deal with in the Euclidean case, is not just this, like the Einstein-Hilbert action, but you have to add also these boundary terms. And I don't want to go to all the details because it's quite different. I mean, it takes some time and it's not relevant for us. But basically, there are some boundary terms which are actually responsible for non-trivial values of this action. And if you do this, you can do this, for example, in Schwarzschild-Cade. So that's this original paper by Gibbons and Hawking in 1977. You can evaluate this in some meaningful way, and you obtain that the total gravitational action will be something like this 4 pi m squared, which is finite. So you found the instantons. Usually people call this kind of Gibbons-Hawking instanton. And that was quite important in understanding black hole thermodynamics. It played quite a big role there. But if you compare it to the situation in Yang-Mills theory, it's actually quite different. This instanton is, when you're doing this for Schwarzschild, definitely not self-dual. This action here is not a topologically invariant, and this action is also not a global minimum. So around 77, 78, so this was paper 77, but around the same time, Hawking has this other paper, like, can we try to find a self-dual gravitational analog of this BPST what we have in Yang-Mills theory? Can we find it in a gravity case? And it was partially done by Hawking himself, but also like 1 year later by Eguchi and Hanson, and they found this Eguchi-Hanson instanton. So the problem, so for example, so when you try to do, so you have this gravitational action here, right? And you want to do what we just presented in, that I just presented in Yang-Mills case. Well, where is the problem? The problem is that you have this Yang-Mills theory, which is usually written like this, like you have action and these field equations. Then in general relativity, you have this GR action plus possibly boundary terms. But then you have these Bianchi identities and field equations like this. Well, the problem which you are facing is that this doesn't look at all similar to what you have here. So there's the idea how to make it more similar. And to make it look at least a bit more similar is to follow this Cartan formalism. So follow Cartan. And basically what you do is you start, instead of working with metric and linear connection, you should start with this tetra one forms. So you just start with the tetra one form, which are related to your metric through this relation. And then instead of linear connection, you will work with this connection one forms. And then from this, as soon as you have tetrad and connection one forms, you can define curvature and torsion. So I'm putting these funny bullets when I mean a Riemannian connection. And you define this curvature and torsion, you define so-called Cartan structure equations. And Cartan structure equations for the Riemannian geometry, which we use in general relativity, are that we have zero torsion. So this zero torsion tells us that we can determine this Riemannian spin connection in terms of the tetrad. And then if we do that and determine the connection, we can calculate the Riemannian curvature two form and the Riemannian curvature tensor from it. So if we have this, what we can do is, well, we can take our Einstein-Hilbert action, which we usually write something like this, and we can write it in terms of this Cartan formalism, and we write it as this curvature forms wedge this star of this tetrad wedge tetrad, which I don't know, looks a little bit ugly, but it's actually this is just the differential form expression for the same what we have usually here in GR. And if you want to make it look more like Yang-Mills theory, you can do this what people call tangent dual, and you must be very careful. This is not a Hodge dual, but you do something what people call tangent Hodge dual or tangent space dual, which just means that you have something which looks like a star operator, so some epsilons, but they are not acting on this mu indices of the form indices of these two forms, but they are acting rather on this tangent space indices, so it's slightly different. But if you do this, then the GR equations, you can write in a language of forms in such a way that you will have this first Bianchi identity, and then the Einstein field equations can be written like this. And this allows us to then consider such solutions which have a self-dual or anti-self-dual curvature. This is what was started by Eguchi and Hanson in 1978. Just show that if you have this equation, it means that you have a self-dual connection or anti-self-dual connection. And then that means that if you have such connection which is satisfying this, it's satisfying the Bianchi identity, But since the curvature is self-dual, it means you are satisfying also Einstein field equation. So you really obtain these automatic solutions of Einstein field equations, which is nice. And then ISGC and Hanson, what they did is they found one example of this, or two examples, I see if I'm correct. They found this so-called Eguchi-Hanson instanton, which is some special solution of these equations, and it plays some role somewhere in Euclidean quantum gravity. Where this is R, and these are the three Eulerian angles on S3. So you will see a lot of this stuff is not done on like S2, which we usually like, but it's actually done on S3. So these are the three Euler angles, phi, psi, and theta. So if you compare the situation, so if you start comparing this, it's like there are some similarities. We are comparing Yang-Mills theory and general relativity. Like you have some one forms as a basic variables, you have some field strengths. Actions look quite different, but then at least you have this kind of self-dual solutions. So here in the Yang-Mills theory, you have the self-dual solutions, which are self-dual field strengths. Here you have the self-dual connections. That's a quite close analog what you have in case of gravity, in the case of general relativity. But there are some big differences. And the big difference is that you must be careful that these star operators are not the same. They're actually completely different star operators. The main difference is that the topological terms in Yang-Mills case are this, and they are directly related for this field strength, self-dual field strength. They are directly they are related to the action. While in general relativity or in Riemannian geometry generally, you have some topological terms which look like this, but they are given by this, which is usually called Euler class and Pontryagin class. So you have topological terms which are quadratic in curvature, but so it looks like Yang-Mills theory, but you must be careful because your action now is not quadratic in the field strength. This is a problem of GR, that your field strength is the linear in your field strength, while in Yang-Mills theory, it's quadratic in field strength. So that means that, okay, you have two topological terms, you have two topological invariants actually calculated from this, but they cannot be related to the action. This action is not related to this in any way. And that means that you lose this very nice connection between your action and some topological terms, which you have in Yang-Mills case. And that's something what I'm trying to improve, or let's say, do it in some other way. So the question is whether we can do this and whether we can solve this problem, find some kind of closer analog of this in a case of gravity. And it turns out the answer is yes. And the solution is that do exactly opposite what we just did in the case of gravity, in case of general relativity. So instead of, as I said, this general relativity is based on the so-called Riemannian geometry. And based on this Riemannian geometry, which means that we have zero torsion and non-zero curvature. So when I say do exactly opposite, this doing exactly opposite has a name, and it's called teleparallel geometry, which means that consider such connection, which now I call omega without these bullets, that it has zero curvature, but it has non-zero torsion, right? So the idea is that if I am on some manifold, I can always define many connections. So this Riemannian geometry is just one connection. I can try to define other connection, which will be defining this teleparallel geometry. So I can have all these different connections living in the same space-time. So we do this, and we can then relay this Riemannian connection, this teleparallel connection, using this relation, which tells us that this teleparallel connection is written as a Levi-Chivy connection plus something what we call contortion one form. This contortion one form is related to torsion. And this is a very important relation because it allows us to basically almost trivially express everything what we have in Riemannian geometry in terms of teleparallel geometry. Everything what is calculated from omega can be expressed in terms of teleparallel connection plus contortion. So if we do this, we can apply this to Einstein-Hilbert-Lagrangian, and we can rewrite this Einstein-Hilbert-Lagrangian as something what we call teleparallel Lagrangian plus some boundary term or total derivative term. So the idea of this teleparallel gravity is that we can discard this term here and just consider this action given just only by this term given by torsion tensors, which, as you can notice, it's quadratic in torsion tensor, and it's quadratic in your field strength. And this is what people usually call, when you define such action by this very specific combination of torsion tensors, we call this teleparallel equivalent of general relativity, which means that since this action, according to this equation here, is equivalent to Einstein-Hilbert up to some total derivative term, it means that it is dynamically equivalent to general relativity. It means that it has the same solutions as GR, same Schwarzschild, same Kerr, whatever. But there is some difference. Usually people say that there is a difference from general relativity. It's differing in the boundary terms because we are discarding this boundary term here. And that's actually true. Yes, if you are comparing this teleparallel gravity action compared to Einstein-Hilbert, it seems that, yes, we are discarding these terms, but then, so there should be some difference, right? But then actually often if you are going to evaluate these actions, and there are some subtleties about like how to do it, you have to either choose these tetrads in a very special way to obtain a finite action. You start to notice some analogies which the situation which we had in the Gibbons-Hawking case of this Gibbons-Hawking or boundary terms and these counter terms there. And basically, you start to discover that maybe up to some factors of 2, which we are now going to explain like why they appear. You will start to see that actually when we are evaluating this teleparallel gravity action, it is often the same as GR action, but GR action, not just Einstein-Hilbert, but also the Gibbons-Hawking-York boundary term plus these counter terms, which are necessary there. So I had recently some papers which are kind of arguing for this, that if you are comparing this teleparallel gravity action with properly chosen frames, whatever does it mean, it's actually equivalent to, it's fully equivalent to GR if we are properly choosing there all the counter terms and boundary terms. But that's actually not important for us at the moment. What is important for us at the moment is that this teleparallel action is quadratic in torsion. So if you consider this torsion to be your field strength, it's actually quadratic in field strength, and that looks like Yang-Mills theory. So there are many interesting stuff, but if it is quadratic in a field strength, if it's quadratic in a torsion tensor, this means that in the language of differential forms, you can rewrite this as a torsion form, which some other form, which we call excitation 2 form. And this excitation form, as the explicit expression is given here, and if you multiply this and look on the components, you will see that it's exactly this. So that means that this is a very nice differential form transcription of this expression which we have here. And you see that it's a product of torsion wedge excitation form. So this means that if you are starting to compare teleparallel gravity and Yang-Mills theory, you will start to see more and more analogies. And the biggest analogy that you have there is that, like, okay, you have this action with this quadratic in your field strengths, these equations. In teleparallel gravity, you can write like this. So the action looks almost the same. Okay, it's not the same, but it looks the same. And the field equations are also very, very similar. So mainly this, you have this Bianchi identity for torsion, which looks like a field equation, which looks like Bianchi identity in Yang-Mills theory. And then you have this, field equations derived from this action, which are the exterior covariant derivative of this excitation form. Plus, you have there some extra terms, which we call energy momentum, gravitational energy momentum current. So you have there some extra term, which turns out to be quite important actually, because it's responsible for some self-interaction in this theory. But anyway, my point, like why I'm interested in this, is when you are writing teleparallel gravity in this language, it's much more similar to what we have in Yang-Mills theory than what we have in general relativity. And basically the idea is now that as soon as you have this, well, you can actually start to question like this self-duality. Like, so we were interested in Yang-Mills case in this self-dual solution, right? But actually, if you go very, very carefully through all the derivation, which BPST, what they did, and you try to construct this self-dual solution, you actually start to understand that it's not important that it's dual, right? What is important is that actually this action is, what is important there is that this action is a product of two forms, right? So basically, or the opposite view which you can take is that if you have this teleparallel gravity action, you see that this excitation form basically plays the role of a star of F. And you can actually generalize this. The point that this H is a star of F, it actually plays a role only if you are proving this BPS bound. It's not important to establish this connection between gravity and topology and your action and topology. And if you are trying to prove this BPS bound, it's actually important. There, the idea that your excitation form is related to some Hodge dual of your field strength is actually important. And this is actually something very, very closely related to what Jakob Ittin, Friedrich Hell, and Yuri Obuchov did in 2017. They have this so-called premetric or axiomatic approach to electromagnetism. So what they do is like, you should start with a field strength. So if you have an electromagnetism, you start with a field strength of electromagnetism, which is just dF equals 0, which is your Bianchi identity, and then your second set of field equations you write as a dH equals 0. And then you can see that basically Maxwell electrodynamics to be just a special case where this excitation form is a Hodge of your F. And then they show that, oh, you should view teleparallel gravity also in this way. So if you do this, then basically you start to realize that this excitation form basically plays the role of the star of F. So that means that you should be able to construct the same kind of instantons like what we did in Yang-Mills theory, right? In Yang-Mills theory, we were considering these self-dual solutions. Since this H is not your star operator of something, it's actually something different. Nevertheless, we can consider new kind of solutions, which I call self-excited solutions, because your torsion form equals to the excitation form. So if you call those self-dual because field strength is a dual of the field strength, I call this self-excited because it's the field strength, the torsion is equal to its own excitation form. And the anti is one which is a minus. So if you do this, you can definitely try to consider such solutions which satisfy this property, and you can do that. And if you do it, you actually obtain something interesting. Then your teleparallel gravity action for such solutions turns into just torsion wedge torsion. And this torsion wedge torsion is actually quite interesting because that turns out to be a topological term as well. And it's comes from something which usually people call Nieyen topological term, which is related to this Nieyen identity, which was discovered in 1982, if I remember correctly. So basically, the idea is that you can immediately show this relation, which is like a two-line calculation, that you are using only Bianchi identities and definition of a torsion, and you can show that this T batch T, torsion batch torsion, is actually divergence of this H batch torsion. So that means that what you can do, and this is called a Niehian term, or this is called Niehian term. Well, it's the same. So, sorry, this is called Niehian term. And this is actually related to something what people call axial torsion. So that means that if you have such solutions in teleparallel gravity, which satisfy this condition of this self-excitement or anti-self-excitement, you can show that the teleparallel gravity action is reduced to a Niehian term. By this Niehian identity, then you can show that this is actually divergence of the axial torsion. You can just apply Stokes' theorem and show that basically the value of this axial torsion at infinity gives you the value of the action. And you can do that, and you will find that this is actually also some topological invariant, or some kind of topological charge. There are some papers by Zanelli and also by me himself from 90s, where they show that this is actually integer. And so that means that you find that these self-excited actions, like the teleparallel gravity actions for these solutions which satisfy this self-excitement condition, they turn out to be given by some unspecified normalization, but they are actually proportional to some integer. And that means that this integer, this Niehian topological number, actually plays a role of some kind of like a winding or instanton number in Yagnell's theory. So if you look at it in components, this term in components is a divergence of what people usually call axial torsion. This axial torsion, which we have here, or here in components, this is actually what plays the role of this Chern-Simons current. So the idea is that now when you compare the situation which we have, it's actually quite interesting because, I don't know, it's of course up to your personal feelings and your personal taste. But when I was saying like, oh, this doesn't look in general relativity, this Eguchi-Hasu construction, it doesn't look very similar to, or it's not a good analog of what we have here in Yagnell's theory. To some extent it is, but it's not as good as analog. My point is that this is much better analog what we have in Yagnell's theory than what we have in general relativity, right? So mainly the field equations, the action is quadratic in your torsion, in your field strength. The Bianchi identity is again a divergence of your field strength. Field equations are kind of similar, plus you have this extra term. And then you can show that mainly you have these topological terms which are quadratic in your torsion, in your field strength, and this topological term you can relate it to your action for such solution which satisfy this, and that's quite interesting aspect of this construction. So I have worked out some example. So for example, when I say that it's easy to find, well, it's a simple problem to be solving this self-duality or self-excitement condition than solving the field equations. Sure, well, it's partially true. It's actually quite difficult to find an ansatz which actually satisfies this condition of anti-self-duality or this self-excitement. And it turns out that you often have to rely on some, okay, I don't know what does it fully mean, but you have to kind of always almost work on S3 for some reason, because you have on S3, you have these so-called Carta-Mauer forms, this sigma x, y, z, which in Eulerian angles have these expressions. And they have some very nice cyclic properties. If you have these very nice cyclic properties, you can actually find some ansatz which very easily satisfy all these conditions which you want them to satisfy. So I was able to find so far one ansatz which satisfies this. So for example, what you do is you take these Carter-Mauer forms, you take an ansatz where you have some function f and g, and you have just the dr, which is your radical coordinate, and these Carter-Mauer forms like this. And then you can show that, oh, this self-excited condition, that the torsion equals its excitation form, is satisfied when this f equals plus minus g prime, where prime is a derivative of this f and g of the g with respect to this r coordinate. So that means that if you take such ansatz like this, require it to satisfy this condition, you find it this, and if it is satisfying this f equals plus minus g prime, then it is guaranteed to be a solution of field equations. So you really confirm that this is a solution of field equations, and it turns out to have a non-vanishing axial torsion. And you can evaluate this axial torsion. So you just take this integral of this axial torsion, use Stokes' theorem and transfer it into some surface term. And then you find that for all solutions where this g goes to unity at infinity, that this is actually just the 6 times the volume form of N3, and you find that this Yang charge is 12 pi square. You can actually also show the Eguchi-Hanson instant is also a solution, but there it's 0. So it's quite interesting. So I don't know how physical is this example, but at least we have one working example where I don't know how physical it is to have something on S3. It's a little bit confusing, I admit, but we have such solution, and we have some working example where this is 12 pi square. We are now finishing with one student, some paper on this. Well, finishing, we are in the middle, let's say. We have some working example where we try to understand properties of the space-time. It turns to be related to maybe it has some properties of cosmic strings, which is quite interesting. So we will analyze it, and hopefully soon we will have a paper about this, but we will analyze what is the really physical meaning of such solution. Anyway, this is just an example that you have some working example where you have a non-trivial medium charge, and it is a solution of your field equations. So just to give you some overview. So basically this was the idea that teleparallel gravity really allows us to write this action as a product of two forms. So then following this example of Yang-Mills theory, really consider such solutions which satisfy this condition that these two forms are equal to each other, plus minus. And then you can show that the action of some theory which is dynamically equivalent to general relativity can be reduced to this Nye-Yen topological term and can be reduced to a topological number. So if you evaluate it for some solution, you can get some topological number. So that means that this axial torsion and the Nye-Yen charge will play basically a very close analog of the Chern-Simons current and the winding number in Yang-Mills theory. And it turns out that people have this. I told you that Yang-Mills theory has 3 nice properties. That you have automatic solutions, your solutions are topological, and they are the global minima. It turns out that if you follow Eguchi-Hanson, you have only one property. That you have these automatic solutions. You don't have that what is actually interesting about them. They are topological and they are global minima. Here, it turns out we have that they are also topological. You can relate gravitational action to some topological term for these solutions. So that's same as in the BPST case, but we don't have anything like that in general relativity, and this is the main selling point from my viewpoint, like what I have tried to achieve. But turns out that the BPST bound we don't have there. You cannot prove the BPS bound, because for BPS bound, it's important. BPS bound would work only if your excitation form would be a star, Hodge star of the torsion. But this is actually compatible with the Gibbons-Hawking-Perry result from 1978, that actually the Euclidean gravitational action should not be definite. Should be indefinite, so it shouldn't be bounded from below, because you have this conformal mode problem there. So what does it mean is that, just to give you some concluding remarks, it seems that teleparallel geometry is better suited for understanding this Instanton structure of gravity than Riemannian geometry. I think this is quite okay statement and not overselling it. It really allows us to explore a topological structure of this gravitational action, which is really interesting. There are some hints of some non-trivial waxing structure of gravity, because as I just told you, we have now a working example where we find that this topological term for this weird ansatz on this S3 sphere, okay, I don't know how physical it is, but it's some working ansatz. We have a solution there, which is 12 pi square. So we have some finite Neayen charge, but then we actually have there also a solution which has 0 Neayen charge. And that's quite interesting, because then you can relate them, and then you find out they are related by some kind of like a large gauge transformation. So you have some kind of transformations which are increasing this Neayen number by some discrete values. That's exactly what is happening in Young's theory, mainly in Charles-Simon's theory. So there you find that this action is changing under some large gauge transformation by some, the winding number can be increasing. That's what I mean by winding number. It's if you do some 2 pi rotation, you always can increase this winding number by 1. It's not so clear yet what does it mean here in the teleparallel gravity case, but we have the analog of that, and we are working on some paper which will explore this. Some applications of this is like, okay, except trying to understand this Instanton structure of teleparallel gravity. I still believe that it gives us maybe another try for Euclidean quantum gravity, that in this language, gravity becomes much more closer to what we have in Young's theory. So that means that we could try to use some techniques. I don't know where we will lead, but at least we could try to understand some problems. Also this conformal mode problem in this language of teleparallel gravity. It's actually quite interesting what is happening there. It's quite technical, but you will start to see why this problem of conformal mode also appears here. But it's analyzed in a completely different way than in a standard general relativity, like what Hawking and Perry and Gibbons did in 1978. So I don't know whether we can resolve the problem, but at least we can try to understand it from some novel perspective. And then, of course, like the same, this was actually done. So these two things, like all the things here, were not done much before, I think. But surprisingly, people already considered and already Eckhart Mielke in 2000 something, and people around Stavrakidis and Peter Shoup and all these people, and the group in USDC in China around Ming-Je Li, they already did this actually, that we can try to construct some, well, we have this Neayen topological term, and this Neayen topological term, let's make it dynamical. So let's couple it to a TGR action, that this teleparallel gravity equivalent general relativity action using some function, and then you will obtain some kind of like a gravitational axiom. And this was already done, but well, it's currently being explored. Let's say it's not fully resolved. But that could be also quite something interesting, like how to obtain axiom-like modifications, but not some QC axioms, but real gravitational axioms based on this construction. Okay, so thank you very much for your attention, and I think that's all from my side.
Thank you very much, Martin, for the nice talk. Yeah, are there any questions from the audience? We have like 4 minutes because the speaker has to leave in. Yeah.
Well, I mean, it can be 6 minutes.
Okay. Well, until, I don't know, someone wants to ask something. Yeah, very nice talk. From the conclusions only. So, like, I understood that there's no analog for the BPS bound here, right? So in the teleparallel gravity. So these solutions, I mean, in the end, you will not be able to say that they are dominant contributions to the path integral,
Yes.
right?
Yeah.
So and what are the possible? I mean, here in the second to last point here, you say that it gives us another try for Euclidean quantum gravity. In what sense? Because it simplifies the language between. I mean, it makes it resemble more Young-Mills, or yeah, why?
Okay, so I analyzed this BPS bound, right? And it's actually fascinating what is happening there. It's everything looks almost the same like in Young-Mills theory, only because you have like 1 or 2 extra terms which are there for some reason, which I still don't understand why they are there. And like everything, the calculation, you can do exactly the same calculation like in Young-Mills case. You just create this. In Young-Mills, how you do it is you create a self-dual until the self-dual part of the field strength. You can do here the same kind of stuff. Everything works the same. Only at the end, if you want to define a norm, you need a star operator, and that kind of screws it up. And so we now understand. So when I say it allows us to analyze this problem of this BPS bound better, is now I'm not able to prove the BPS bound because I see what is destroying this BPS bound there. I have some specific expression for this term which is destroying this BPS bound. And maybe this will help us to understand the problem better. I don't know.
Okay. Good, thanks.
So you can, because how actually this paper by Gibbons, Hawking, Perry, what they did is like, oh, they just show like if we potential, we can make it infinite this action. Here you understand what exactly.
There are some interruptions, so I cannot hear you very well.
Yeah, so maybe you can try to understand the problem from the perspective that maybe you can try to find some cases where these terms which are destroying the BPS bound are, let's say, 0, and you can maybe obtain some kind of conditions under which you can obtain the BPS bound.
I see. Good. Any other questions from the audience?
Yeah, I can ask one. Thank you, Martin,
sure.
for the talk. So I'm wondering, do you think that it is possible to repeat a similar analysis using the language of non-metricity instead of torsion?
The non-metricity is kind of weird, yes. I think non-metricity is only one form or something like that, right? So I don't know. Logical term coming from non-metricity. That's actually also, we don't know any Nieyan analog in non-metricity case. And mainly the non-metricity itself, I think it's only one form, right? So you cannot have something like 1 form equals 3 form. So then your action must be something like 1 form times 3 form or something like that. And it's kind of weird. Like I already thought about it, but I didn't come up with anything useful, let's say.
Yeah. Thanks. So it seems that the torsion language seems to be more suitable, like building the connection between gauge and gauge gravity duality.
Yeah, yeah.
In general. Okay. Thank you.
Any other questions? Yeah, there's one in the chat actually. So Amoeba says, can the near-Young term be related to some form of the quasi-local energy?
Well, in some way, yes, right? Well, I don't know whether energy, but in some way, not directly, yes, you have to derive it from there. So you could do it for this kind of terms as well. Like the same, like you are deriving some kind of energy for from Gibbons-Hawking or something like that. You could try to do it here, but it requires some work. Like it's action, right? So let's see.
Good. Well, I guess there are no other questions, and in any case, Martin has to go. So yeah, once again, thank you very much, Martin, for the nice talk. Let me stop the recording.
Okay, thank you.